So I guess I just picked, since it's composed of 3 parts, I just picked the first part to be this lecture, which is a great start. So I'm going to talk about something which is maybe sort of related to where Jaroslav left off. So the last thing he said was that, well, we have understood the kinematic structure, a 3-point and 4-point, but in order to understand gauge theory, we also have to introduce color, right? So I guess I'm taking off from that statement. And also, as Jaroslav said, I'm not necessarily going to be in 4-dimension in this talk. In fact, almost nothing I'm going to say today is going to depend on the dimension. So yeah, this is some generic analysis of how color enters gauge theories and how it's related to kinematics. So let me just say a few words, trying to, right off the go, trying to capture what color kinematics duality is. It's a bit mysterious, so let me try to say some generic statement trying to capture it. So this is an observed structure. It's a bit of weird chalk. In many gauge theories. That link color and kinematics, degrees of freedom, and it's, let me say what I mean by color here. So this is some internal space degree of freedom, so internal internal space, and this is of course external space-time. And this is hidden in standard QFT. Well, put it here, QFT. Formalism. But becomes more apparent in scattering amplitudes. And I say more apparent is because, well, it was for a long time it wasn't apparent in amplitudes either. So it's only in the last 10 years that it has become apparent. And I should say this is the, well, it's a long version of trying to explain what color kinematics duality is. Maybe the short version is that, well, we don't really know what it is, but it's cool. And the reason why it's cool is because we don't really know what it is, so it's an open research field. And there's a lot of questions which are still, people are still trying to answer. Okay, but just let's look at gauge theory very generically. So gauge theory, we can roughly try to understand by just analyzing the symmetries of gauge theory. So we know that there's going to be some color group, which typically we pick to be SU and C for simplicity. Of course, it could be something different, but let's think of that in this case. And that's the internal degrees of freedom. And then, in addition to that, we of course have the space-time symmetries, which is Poincaré. And furthermore, we can try to understand the building blocks that we need for amplitudes by just thinking of what goes into these symmetries. For example, in the Lie algebra gauge group, we're going to encounter generators, and we're going to encounter structure constants. I'm going to come back to them later. In the Prague part, we're going to encounter momentum, which we already saw a lot in Jaroslav's talk. And there's also, of course, the Lorentz part. Now for particles, we often consider the little group part of this Lorentz part. So this goes to the little group. And in that case, we're using, for example, polarizations to describe the little group, or as we saw, spinors. So polarizations. I can put it here, I guess. Or spinor helicity. Which we already saw in Jaroslav's lecture. And of course, the momentum generator just corresponds to the particle momentum. And these guys are a function of the momentum. But so this very generic analysis of the symmetries also leads us to think about amplitudes having a similar structure. So on just general ground, we expect that amplitude should be a product of something carrying this object, the color objects, and the kinematic objects. So on general ground, we should expect that maybe it's a sum of something, a color part, color factors, times some kinematic factor, which I'm just going to call AI here, right? And it's a very generic formula. I'm not really saying what this sum is over, but this is a first flavor of what we will see shortly called color decomposition. Essentially, we're trying to isolate the color dependence of the amplitude into some coefficients, and then we have sort of a remainder, a kinematic remainder left over that we typically going to call a partial amplitude. That's why I'm calling it A here. And let me switch to the next one. All right, so let's consider the color factor here. So I'm going to keep calling color factor by the letter C. And I here is just some index that runs over the different color factors that I have. So it's a function of the generators that I have, and let me just consider it as a set of generators, each maybe have one of each for each particle. Let me be a bit schematic at this point, but it's going to be a function of generators, possibly a function of structure constants. And there could also be other color tensors, but let me just consider the simplest one, which are these two. So it's a function of only color. And then we have a partial amplitude. I will get a bit more concrete shortly, but for now, we're just going to think of it as a function of momentum, and there could be many momentum depending on how many particles you have. There could be, as we saw, polarizations. And there could be spinners, as we also saw in Yaroslav's talk. So this is a typical objects that we consider it to be a function of. So only kinematics. And so now I'm going to try to discuss these two functions in some detail. And in particular, I'm going to start with the easy one, which is the color part. And so for SU and C, well, we know that that's a Lie algebra. Well, it has a Lie algebra, the group. And so using that Lie algebra, we can essentially compute color factors, which is somewhat trivial. I say somewhat trivial because, you know, the theory of Lie algebras and Lie groups is, you know, standard topics which has been known for a very long time. So there's no real mysteries going on there. Of course, when you sit down and do things in practice, it's still, you know, something you have to, well, you know, practice and you know, until everything becomes clear. But the kinematic part, so which I said is related to the Poincare symmetry, also related to gauge symmetry. Locality and unitarity. Which is all ingredients used to compute the partial amplitude. This is non-trivial, very non-trivial. Let me say very. In the sense that you have to put in a lot of work in order to compute these objects, and you know, to a large part, you know, Amplitudes community focuses on computing such objects because, you know, the color dependence is typically trivial. And maybe some of you might be puzzled, why did I put gauge symmetry here? Because usually we think of that as being the gauge symmetry. And the reason why I did that is because here I'm just thinking of the global part of the gauge symmetry. So it's just, you know, understanding Lie algebra, which is a global part, whereas the local part of the gauge symmetry has to do more with the kinematic, you know, dependence, because that, you know, the local part is supposed to be how things vary when you go from point to point in space-time, so it has nothing to do with kinematics. All right, so maybe I can ask if there's any questions now before I go into detail about how the color factors are determined. All right, I think it's still a bit too high. There we go. So yeah, as I said, color factors are built from generators of the Lie algebra, TA, and or structure constants. FABC. And the reason I say and or here is because, well, they're not independent objects, they're related in particular, the defining relation for the Lie algebra is this. And actually, what I'm going to do here is I'm going to forget the usual I, and let me put a tilde here, because this is, I'm using a slightly non-standard convention where my structure constants are imaginary. And the reason for that is, well, it just makes some things simpler later on. That's why I put the tilde there. So it's more along the math literature convention. But yeah, so they're related. So in particular, it's possible that you can eliminate one in favor of the other. For example, here's a relation which I'm not going to derive. Maybe I should leave it as a homework. So here is a relation between T and F, but you can also eliminate F completely by doing this substitution, where you write it as a commutator of two generators, TC. I guess usually when this formula is introduced, the lecturer shows how it's derived. I'm not going to do it here today because, well, I'm not primarily talking about color decompositions and so on. So that's why I'm not going to necessarily derive it, but I welcome anybody to try to derive this formula from that formula. And one thing that you need to use is, for example, you need to define what your normalization is of two trace of two generators. So it's a common convention in Amplitudes community to pick it to be that the trace of two generators is just delta AB. But essentially, this formula follows from that, using this as an intermediate step. Furthermore, there are relations between the FABCs themselves, which you might recognize as Jacobi relations. So, for example, this is a quadratic relation in terms of the structure constants. And so here, one way to understand the Jacobi relation is to just say that I'm going to add the cyclic permutations of three of the indices. So let me pick B, D, and E. So this is just plus cyclic of B, D, and E. So pick any of the three free indices and add the cyclic permutations, and that thing is going to add up to 0. That is the Jacobi identity. Yeah. This comma, you mean? Yep. Thanks. I guess I'm notorious dropping and inserting commas where they should not be, maybe, yeah. All right. So all of these relations mean that you can use one or the other variable. There's one identity which I'm not going to explain here because I'm not going to need it. But those of you who are expert might know which one it is I'm talking about, but let me not mention it by name. So what I'm going to talk about is maybe I need a new board again. I'm using that up pretty quickly. So just like Jaroslav was considering all particles being of the same type, I'm going to consider all particles being adjoint here. So I'm not going to include, for example, quarks. So let's just assume that everything is an adjoint. So for all particles, in the adjoint representation, of the gauge group, you can write your color factors as functions of FABC alone. Because obviously, if everything is then adjoint, you might know that the Lagrangian is written entirely in terms of the structure constant. And so therefore, your Feynman rules are going to be entirely written in terms of the structure constant. So that means that your color factors, which are just some decomposition, is going to be a function of only the FABCs. Nevertheless, in Amplitudes community, we often sometimes change which variable we use. So there's an option here that you can also write them as function of only the generators. And one example was here that if you have a single FABC, you can eliminate it in terms of generators. I'm not going to show all the steps in doing this, because I'm going to only talk about color factors as functions of FABCs in this talk. I think maybe in later lectures, you probably will see where amplitudes are functions of the generators. I think, except for the derivation, how to go between the two, you're not going to lose very much by me considering them being functions of FABC. Right. How do we know which particular combinations of FABC appears? Well, as I said, the appearance of color is kind of trivial. If you just study, for example, the Lagrangian or the Feynman rules, it's kind of apparent from that stage what you're going to get. So just from looking at the Feynman rules, give you that you're going to get all sort of contractions of FABCs corresponding to the diagram that you're looking at. So for example, in some arbitrary labeling scheme, I might say that my first color factor is going to be something that looks like A1, A2, B. So here, the indices on the A's are my particle numbers, and B here is just some internal index. That's why I don't put an index on it. So B, and then we have maybe particle, then we have particle 3, then we have a dummy index, and maybe A4, a dummy index, and so on, until we have the last one. Let me call the last one Z, dummy index, AN minus 1, AN. So here N is the number of particles, for example, and they're all contracted. All the FABCs are contracted, and that is kind of apparent if you just look at, for example, Yang-Mills Feynman rules, that you will always get that indices has to be contracted. You will never get a product of FABC where indices are not contracted. And I can just do this brute force. I can label all the color factors that I find, and let me just indicate this schematically. So there's going to be a bunch of Fs. This is very schematic. And the question is, how far do I need to go before I have exhausted all my color factors? And the answer is that you have to go to 2n minus 5 double factorial, and I will explain that number. Yes, how do you get this number? Well, so that is just the number of cubic diagrams that I can imagine at n point, right? So the number of cubic diagrams so for n equals to 3, well, there's only one cubic diagram I can draw, right? So that's 1. At n equals to 4, there are 3. Let me just draw one of them as an example. But as obvious is 3. There's 3 permutations of this. We already saw them. It was the S and T and U channel. For n equals 5, well, let me draw one diagram. And then I can say that all other diagrams is just a permutation of this. And you can work out that there's 3 times 5 such diagrams. It gets a bit more complicated at n equals 6. You can draw this diagram. And you can also draw another topology, which is this guy. And so you have to consider all permutations of those. And if you work out the number, you're going to get 3 times 5 times 7, and so on. And then at n point, you're going to get 2n minus 5 double factorial. Okay, so let me explain the logic here. The logic is that FABCs are cubic. So that's why I'm only drawing cubic diagrams. As I said, the FABCs has to be contracted. Therefore, I'm drawing connected diagrams which are cubic at a given multiplicity. Now, how do I get the number? Well, so the number is recursively obtained. So in order to get 4 point, I can just consider how many ways can I insert the fourth leg here. So there's 1, 2, 3 places I can insert the fourth leg. That's why I get 3. Now here I can consider how many ways can I get 5 point by inserting the fifth leg. There's 1, 2, 3, 4, 5. That's why it's a 5. Here again I can consider how many ways can I insert the sixth leg on this diagram. 1, 2, 3, 4, 5, 6, 7. So that's this number 7. So if you just do this systematically, you get a unique set of diagrams, and it's 2n minus 5 factorial, which is just the product of all the odd numbers. So that's what we're seeing here, right? So we know that in my amplitude at endpoints, I will see this many color factors. Of course, they're not really going to be independent. So they're not independent. Because of, for example, the Jacobi entity. In fact, the Jacobi entity is the only one that's relevant here because all the other ones involve T. And as I said, I'm already considering color factors not made out of T's. So the Jacobi identity is the only one that imposes relations among these cubic graphs, or the color factors. Let me try to illustrate how you can systematically use the Jacobi identity to eliminate redundant diagrams such that you get into a basis. Let me raise the board slightly. All right, so consider some generic diagram. And I will draw it in a particular way, even though you can imagine that it's quite generic. So imagine we have a bunch of legs here. Maybe I should use a different color. And then we have maybe a fork, looking like this here. And then we have a bunch of legs here. So the dot, dot, dot means here that there can be any number of legs over there. Now, if I focus on this red part of the diagram, I can use my Jacobi identity here, which is basically a 3-term identity between 4-point graphs. So I can use an identity to eliminate this particular subgraph. And diagrammatically, what you're going to get is the following diagram. where the red has now become this part of the, oops, maybe it's a bit big. So that's one, and then it's a three-term identity, so I need a third graph. And so this is like a non-planar graph. Right. Yeah, so this is just the Jacobi identity implemented at the graphical level. And maybe to be clear, I should have actually drawn the Jacobi identity graphically. So let me see, just draw it as the way I'm going to do it later on. So we can draw this like this. So this is A, B, D, E, plus, let me draw it like this, whoops. Still A, B, D, E. And now I'm inclined to put a minus sign there, but I still going to convince you that it is just plus cyclic, but graphically it looks nicer if I put a minus sign there. So this is the graphic implementation of the Jacobi identity. And well, okay, sometimes, you know, I know many people have troubles moving graphs in their head, but I guess you have to move this graph down here and convince yourself that these three graphs are the same subgraphs as I drew here. It's not apparent, but it is true. And this minus sign here is basically this minus sign here in the proper way of drawing it. Yeah. All right, so this was just an example of one family of graphs. Of course, you can make it more complicated. You can add more graphs up here and so on. But the general lesson of this is that you can always reduce. If you have a graph which has like a fork sticking out like this, you can always remove it such that it disappears, right? And then you get this kind of graphs that we call, well, they have many names, but one name is a half-ladder graph. I think historically it was also called multi-peripheral graph. So you can convince yourself that this is a systematic way of eliminating all redundant color factors and putting them in a basis. And this basis is called the half-ladder basis. I'm not sure I'm going to fit much here, but let's try. So this is the half-ladder color factors. And let me simplify the picture a little bit. So let's just draw a straight line at the bottom. And then we're going to put leg 1 and leg n. So we're going to fix leg 1 and leg n. And then we're going to consider legs sticking up like this. And we're going to call them sigma 2, sigma 3, sigma n. Well, let's put this one here instead, sigma n minus 1. And so these are permutations. So sigmas here denote permutations. So that means that we're always going to consider leg 1 and leg n to be here. But this could be any leg. So that means that there's some permutation. And as I said, this is just our expression in terms of FABCs. So it's A1, A2, sorry, this should be sigma 2. B, FB A sigma 3 C and dot 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 FZ AN minus 1 and AN. So this is just my definition of this. This color diagram, it just means this string of FABCs contracted together. And I can also introduce a notation for that. I can just call it C, which is a function of 1, comma, sigma 2, sigma 3, sigma n. And I can also, sorry, I forgot. Sorry, this should not be sigma n, this should be, sorry, this should be sigma n minus 1, so this should be sigma n minus 1, and then the last one is n. So I can also shorten this notation and just call it color factor of 1, sigma, and n. So this just means that I have fixed leg 1 and leg n, and then I'm considering a generic permutation, which is denoted by sigma, to be in between. And so this is a permutation of n minus 2 elements. So that's, therefore it belongs to Sn minus 2. So Sn is just a permutation group and with this many elements. So that's a standard notation. And that means that are precisely n minus 2 factorial terms in amplitude. So that answers the question to that formula, what is I running over? Well, if you want to put the color factors in a basis, then the sum runs over n minus 2 factorial, where n is the number of particles. Or if you don't want to put it in a basis and just put it in the most general representations of FABCs, then it's this size basis, right? But yeah, so that clarifies the formula up there. And now we can then write a clearer version of that formula. See if I can squeeze it. I don't know if it's too small here in the corner. Maybe I just erase this part here. Yeah, so what we led to here is that we can write a nicer formula of that amplitude here. So the full color-dressed amplitude, or the full amplitude, is just a sum over sigma, the permutations, so they belong into Sn minus 2. And then we have the color factors that we just call C of n, so of 1, sigma, and n. And then the partial amplitude, well, so the partial amplitude was labeled by the same index, so we're going to use the same notation, 1, sigma, n. And you have to remember here that sigma is basically a string of elements, or a sequence of elements. This formula has a name, and I should certainly write out what the name is, because Lance is sitting in the audience here. So this formula is called the DDM formula. And I think the reason it has a name is that its origin was it was non-trivial to derive it. I mean, now we consider it to be trivial in some sense, but at least when it was first derived, it was like a really cool new result. So this stands for Del Duca, Dixon, and Maltoni. All right, and I can also make it a bit more exact by putting the coupling dependence. So typically we put G n minus 2 here, and now G is the coupling, for example, if you're considering Yang-Mills, this is Yang-Mills coupling. So it's not the coupling that Jaroslav had. It differs by square root factor, but or you know, well, yeah, what he called G was the square of this one. But anyhow, this is a fairly conventional normalization. And so here, A 1 comma sigma n they're typically called color ordered. Partial amplitudes. And sometimes they're just called color stripped amplitudes, which makes more sense in this context because all we did is that we just consider all color factors and then we strip them off. So therefore they're called color stripped amplitudes. But the traditional name is color ordered because usually they're derived from the trace representation, so where the color factors are written in terms of traces. I think I erased that formula. And in that case, there's an ordering, a cyclic ordering, which is important. So that's why that is emphasized in the name. So I should say that here, I mean, I'm not going to derive that because it's not part of my lectures, but these are the same partial amplitudes as in the trace representation. Or trace decomposition. And maybe that doesn't make any sense to people who doesn't know what it is, but I'm sure a fair number of people in the audience know what trace decomposition is. All right, any questions on color factors? Yep.
Is this only valid then under the assumption that we're working with fields in the adjoint representation?
Yes, so very importantly, which I might have erased, I said that I'm going to consider adjoint representations fields or particles, and as long as you maintain that, everything I said here is true. Because I didn't use any other properties. I didn't specify the space-time dimension. I didn't specify the Lagrangian or anything. I'm just assuming that my building blocks are FABCs, which is true of any theory in the purely adjoint. Oh, sorry, with maybe one exception, and that you could possibly have a symmetric DABC tensor in some theories. So maybe that one is not included here. Yeah, so maybe I should be more clear. Purely adjoint theories which only have FABCs, and to be even further clear, to only have FABCs and only have single trace interactions in the Lagrangian. Those of you who know might also know of certain theories which have multi-trace interactions. So yeah, okay, I'm not considering that here because I said I'm only considering connected diagrams. So that implies single trace interactions in the Lagrangian. All right, but this is the reason I'm talking about this is because this, of course, is precisely how Yang-Mills work. So we can just put Yang-Mills here, and that's maybe the most important theory. So the Yang-Mills has this property, but there's also a ton of other theories which has this property. Also, for example, if you have super Yang-Mills series where you have adjoint matter, all of this goes through unchanged. All right, any other questions? Yeah. Yes. So it's confusing that the bases disagree. On the other hand, I said that if you just use all color factors, the basis is even larger. So just because you have put your color factors in some basis or pseudo basis, it doesn't mean that you cannot go further and reduce your amplitude. Now it's true that if you have no other properties than a theory which have adjoint color factors, the properties that I said here, then you can't go further. So this is the true basis if you have no other properties that you can exploit. Now Yang-Mills does have other properties, so we will see a smaller basis shortly. But for now, the only thing I used was the Jacobi identity and the fact that FABCs had this pictorial representation as connected diagrams, then you cannot go further than that. That is the basis, right? But of course, what we'll find is that this A here has special properties, and that will actually allow for a further reduction. And this is also what happens when you consider the trace decomposition, is that you get a larger set of partial amplitudes, but they're not independent, right? So that's why it allows you to go even further in the reduction. Okay, many questions? Yes. Yeah. So the next thing I'm going to talk about is A. So maybe if you just wait, I will discuss that. And that, as I said, this is, I was about to say this is just trivial color, but of course you should never say something so trivial, especially when you're lecturing for students. But it is, it is trivial, right? I mean, I think anybody can, spend a few days on this and it's trivial, right? But AI, the partial amplitudes are very non-trivial, so that requires, much more detailed analysis. Right, I think there was one more, yeah. Yes, well, so it's because of, I didn't go through the derivation here, but I think you could convince yourself that if you have this type of diagram, you can always reduce the fork to this, but of course 2 forks here that I'm not touching, right? And that basically means that there are some legs which are special, and it turns out if I draw it like this, is more apparent that is the first leg and the last leg which is special. And so essentially, you pick any 2 legs. I mean, I picked leg 1 and leg n, but you can pick any 2 legs, and you can sort of stretch out the diagram. And then when there is like a fork here, you just use this identity, which means that you can stretch it longer and longer, right? And eventually, when you have used this identity multiple times, you stretch it as long as possible. And that's why these 2 legs are at the very end. But there's nothing special about leg 1 and leg n. Pick any 2 and you can do it, right? So, and I think this, once you think about this picture here long enough, it will be clear. But I think this is actually Lance's argument. I think before Lance made his argument in this paper here, it wasn't super clear what was the preferred way of doing it, I guess. At least not to me. Well, it's a pretty old paper, so yeah. Any other questions? Yeah, all right. So I think I should move on to the kinematic part. Maybe I should erase this one so you can see it still. So in some sense, of course, Jaroslav's lecture was all about kinematics, right? So you might think that I'm going to cover roughly the same thing here, but I'm basically going to keep going where Jaroslav left off. Not in terms of spin-helicity, but I'm just going to say some generic properties of this kinematic part of the amplitude, which saw only a tiny bit when he discussed the 4-point amplitude. So let's discuss the partial amplitudes. So the partial amplitude, which I call 1, sigma, n, and per sigma here is permutations of the numbers 2 through n minus 1. The first thing to note is that this is actually a gauge invariant quantity. So it's a gauge invariant function of momentum for all the parts. So I here, well, I used I in multiple contexts, but I here is the particle number. So you have momentum, you have polarization, you have maybe a spinner, which can also carry an I index. And why is it true that it's gauge invariant? Well, so we know that the full amplitude is gauge invariant. And now I might have, yeah, so the full amplitude is gauge invariant. And now we have put it in a basis, which is a true basis of the color factor. That means that its coefficients must be gauge invariant too. There's no way, if some of the partial amplitudes are not gauge invariant, there's no way that the full amplitude is going to be gauge invariant because each coefficient C is independent. So there's no way that can happen unless the partial amplitude is gauge invariant. Furthermore, we typically call partial amplitudes planar, meaning that you can completely calculate them using planar Feynman rules or color order Feynman rules. So when you draw the graph in the canonical ordering, all diagrams will be planar. They will not be in the non-planar crossings. And furthermore, maybe one thing related to planarity is that they're cyclically invariant. So the full amplitude is, of course, full permutation invariant. And some of that permutation invariance is inherited by the partial amplitudes, and it becomes cyclic invariance instead, rather than full permutation invariance. So this just means that, well, if I write out all the sigma, for example, in the canonical ordering, I can just cyclically permute my labels. And it's still the same amplitude. Furthermore, there's a reversal symmetry. Let's see if there's some better shock here. So reversal symmetry is I just flip the order of my particle labels. So for example, if I start with n minus 1, all the way down to 2 and 1, I can just flip the ordering. 1, 2, 3, n minus 1, n. At the expense of maybe putting in a sign. So there's a sign here that depends on the multiplicity n. Actually, I should also apologize at this point. I use n for two different things. Which, okay, I haven't not introduced the other n, but that's fine. Shortly, I will use another n. But anyhow, so the multiplicity n here might introduce a phase, which is just plus or minus 1. And it can understood, for example, at 3 point is just because FABC is antisymmetric, so that's why you need an antisymmetry here if the permutation is odd versus when it's even. Okay, I should say that these symmetries are not apparent from the way we define the partial amplitudes, because we always fixed particle 1 and n, and now I'm actually considering a different permutations than that, so it's not apparent from the derivation. It is apparent if you derive this from the trace basis decomposition, which I unfortunately don't have time to do. So I think at this point, maybe just I have to take this for granted. I think Jaroslav was supposed to do this, but he did not get there, I guess. Yeah. There's also an identity called U1 decoupling identity. And it's called U1 decoupling identity because if we consider a gauge group which is U1, essentially having photons, we know that there cannot be any interactions between photons, so the amplitude has to vanish. The question is, how does that vanishing look like in terms of the partial amplitudes? Well, let me write it out what it is, and then I could explain it further. So essentially, it just means that you pick a leg, for example, leg 1. Maybe I should use a different color. So we pick one leg being special, so it's pink, I guess. And then we maintain the ordering of all the other ones. So, and then we just insert this leg 1 in all possible locations. So we're going to have one which starts with 2, and then 1, and then 3, up to n. There's one more, a 2, 3, 1, to n. And last term is where we have moved leg 1. Maybe you can either move, well, you can't move it all the way because that's just equivalent to that by cyclicity, but when you put it in the second to last slot, so 1, let me use pink here, n. So the sum of these diagrams is 0. So essentially it's just inserting leg 1 at all possible location and not overcounting because of the cyclic properties. And you can convince yourself that essentially, well, I'm not sure if that's so easy to convince yourself that that's the correct interpretation of photon decoupling or U1 decoupling. Yeah, let me just leave it like that. You can ask me more question where this comes from if you have questions. Okay, so then it turns out that this identity is part of a larger class of identities. And this carries a name or two names. So they're called Claise-Coif relations. Or I don't know, I have to apologize for the Dutch people. Everybody mispronounces the name here. I think Coif maybe is better. And so I can write up the full formula for the reduction. So assume we have leg 1 and leg n at these positions, and then we have two sets of elements, alpha and beta. Let me just put a underscore just to emphasize that this is a set. And so we can move beta past n by this following formula. So there's a minus sign to the number of elements in beta. So let me denote it by that. Then there's a sum over sigma A1 comma sigma comma n. So this is our basis. And what is sigma? Sigma is the shuffle product between alpha and beta. And so shuffle product is simply you have two sets, alpha and beta. Think of it as two halves of a deck of cards, and you shuffle it in all possible ways. This is what this shuffle product means. So all orderings where you have combined alpha beta that maintains the order of the alpha elements and the order of the beta elements, but not the relative order between the two sets. So this proves that, well, given this formula, if this is true, you can convince yourself that you have put yourself in this n-2 factorial basis. Yeah, so essentially this formula implies that the partial amplitudes have a basis of n-2 factorial independent amplitudes. And it shouldn't be a surprise, because that's exactly the same number as we got by analyzing the color factors, right? And so these numbers has to agree. So Claes-Korf relations are just implementing the fact that our notation had some redundancy, but that redundancy can always be eliminated and put yourself back in the basis. So yeah, so the conclusion is same basis. Basis is same as the color factor basis. Which it has to be by consistency, but it's nice to see it explicitly in this formula. And am I running out of time, or? Yeah. I mean, it might be a nice place to break, I guess. I think if I'm gonna do anything more, I'm probably gonna need 20 minutes for that, I guess. Yeah. So maybe I can just stop here and see if there's questions, I guess.
Okay, some urgent question.
Yeah.
Does the sign not depend by alpha?
Sorry, I think I screwed up the formula. No, it does not depend on alpha, but I missed one thing in the formula which is important. It should be beta transpose over here. So it's a set to just transpose, reverse the order in this. Yeah, so it does not depend. And you can kind of see that, well, it's obvious. Well, I mean, if beta is empty, then the formula becomes trivial. If beta contains one element, then it becomes the U1 decoupling identity, actually. I'm not sure if that's enough to deduce that it does not depend on alpha, but yeah, it does not depend on alpha.
There was another question.
Yeah, okay, I forgot the transpose. Yeah, that's important. Any other questions? Yep.
So just any explanation why the amplitude is planar?
Why is it planar? I think that's maybe most apparent when you use the trace basis representation. Let me see if I can try to understand it. Yeah, I don't know. Lance, do you have a good answer why this comes out to be planar? Yeah.
I think if you put the draw a Feynman diagram where you don't have the external legs ordered 1 to n, or if you order them 1 to n and you cross over to make it non-planar, you'll go into a different partial amplitude.
I think it's clearer in the trace decomposition, which I didn't explain here. Yeah.
Might be a little clearer.
Right at the beginning, did we consider that the external legs or particles are on-shell, or this is
Oh,
the restriction?
am I considering on-shell external legs? That's what
Yeah, that's the question. Yeah.
Yeah. Essentially, anything I said goes through even if they're off-shell, except that, well, it's only true that it's gauge invariant on-shell, of course, right? But I mean, ultimately, I'm going to talk about amplitudes, and therefore everything should be on-shell. But most of the steps in the derivation didn't crucially depend on on-shellness. Yeah, only the fact that these functions are not pleasant if you're off-shell, so they're only going to be nice functions if you're on-shell, right there.
Okay, let us postpone all questions to. And yeah, thank you, Henrik, very much.
Yep.
So let's follow Jaroslav probably. He knows the way where to go for lunch. There will be a queue, but I think they will manage quickly, I hope. And yeah, let us gather at 3 p.m.